In this video, we would like to discuss midterm exam. The reason it is, since this is an online session, and really would like to reduce the confusion in your side. I would like you to feel comfortable and enjoy the work. Okay, so from the canvas, definitely you can go to the midterm exam, and let me explain. And for me, I want to check different questions. These have a choice question. In the choice question, of course, we want to make sure you understand specific algorithm we discuss. Let's make it a little bit bigger. How do you think? Yeah, much better, right? And then in the previous one, and also we want to check what is the master method you can use to infer the runtime for recurrence relationship. And then so also I think this is the choice question. In the Horn's partition of the quicksort algorithm, if the scanning index stop where point to the same element I equal to j, the value they are pointing to must be equal to the pivot. So we say that is true. Okay, oh, sorry, I should not tell you the answer. Okay, so the other one that is all corresponding to the runtime analysis, and we check the quicksort, we check the different recurrence relation. For me, in this video, I want to explain several, the algorithm-based question, algorithm design-based question. First, let's take a look. The question 7, design O log n algorithm to find the first or last occurrence of a given number in a sorted array. Since this is a sorted array, definitely we consider binary search tree. So in the binary search tree, this is the question. Let's write it down here. So this is for question 7. Okay. And then since this is the sorted array, given the sorted array, right? And first step, we build a binary search tree. Which corresponding to, let's draw a picture. For example, right? We have 3, 5, 7. Binary search tree corresponding to tree structure. Every element is larger than, every element is smaller than. I think here maybe I just think about the binary heap. So this corresponding to every element here in the middle of this element should be larger than or equal to. Here we to simplify, we use the just strict comparison. So this number should be larger than this one. For example, you have 10 here, right? Then in that case, this number should be smaller than this number. For example, 7. And this number, the right child, this is corresponding to, since the binary tree, right? First, it should be binary tree. Every node has not more than 2 child nodes. And this number should be larger than, this root number should be smaller than or equal to the right child node. And for example, this is the 21, right? And you can imagine for each this one, they follow the same procedure. This number larger than what you have this number, for example 5, and this number should be smaller than this number. And this number is in the left branch of this 10th root node. So this number should be smaller than this number but larger than this number. So this is corresponding to maybe 9. And then we can see here it is this binary search tree which you can treat each nodes as the splitter. And this splitter divide the whole sequence arrange into the whole integer range into different sub-range. Right? And in this case, in this part, all the left this one, all the left the subtree should be smaller than 5. And between here, this is a 5, 7, and this is a 7, 9. If you say, we just talk about the range, right? Then this is 7, 9, and this is the line 10, and this corresponds to this one, right? This is a 10 to 21. This is a binary search. In such case, use this tree structure and use each node as a split of this tree structure. Arrange the elements into different ranges. Then later, when you insert elements, you need to make sure you insert in the specific range, right? For example, if you have to insert 8, let's say insert 8, and where do you think to go? So you should be stay here, right? In which range? In this range, right? Should it be larger than 7 but smaller than 9, right? So it could be 8 here, right? Should be in this range, right? Should stay in this range between that, right? So if that range corresponds to, you insert between each other, between these two elements, you can only insert for 7, but you can insert in the left child of 9. For example, if we want to insert maybe the 18, and 18 should be stay in the range, this part, right? So it means 18 should be here. Let's say insert 25, and 25 should be in this range, which is 21 through the infinity, right? This range. So in that case, 25 should be here. Once you insert more elements, it cuts into even smaller sub-range, right? So this is corresponding to 10 to 18 and 18 to 21. This is the binary heap. And also, this is this is a binary search tree. And here we ask you, find the first or last occurrence. And in this corresponding, you can set the equal sign. And here we have to go from the root, and based on the ordering property, you check if the search k given number is smaller than this one, go to left. And you follow the same procedure, right? If it's always you find first, and if even that is equal sign, you go to left. If this is equal to the root, the current nodes you visit, then if it's check the last occurrence, you go to the right side, right? So this is you just update, adapt this binary search in how to insert the element in the binary search, and analyze this method, and also use the search method in binary search tree, adapt this one. So definitely this is the O log n, because as we mentioned in the binary search, since it's follow the binary, it's 2 nodes, right? So the height corresponding to the how many nodes in each level, and we see in the binary search tree, the height is O log n, not beyond that. So this reason, when you search from the root to the leaf nodes, that is O log n. This is corresponding to average case is O log n. Okay, please write down your answer and reduce the problem to the one that we can use a well-studied algorithm to solve. And of course, this binary search tree. Explain your algorithm in the text or show the code. Add time efficiency of algorithm. Okay, now let's take a look. Next one. This is a question 8. Right? And assume that we need to search for a given number in an n times n matrix in which every row and every column is sorted in increasing order. So it's very similar to the younger tabular. Design ON runtime. Please write a short code and give a brief explanation of your design. This is the young tabular question actually, right? Because it follow complete the problem and complete this property, and also the ordering property satisfy. And so here, just like we mentioned in the assignment, it's ON, because n times n, right? It's ON runtime. Give the time complex analysis for best case, worst case, and average case. This corresponding since you want to search a given number in the Young tabular n times n matrix. Best case is, of course, is O1, right? Because constant in the very beginning, the left top, it just happened to be the target. Worst case corresponding to, that doesn't exist in the younger tabular. So it's n times n or n times n. Okay, I should not tell you the answer. And for average case, you use a probability. You check this target could happen in each position if that is exist there. If it's not exist there, then in that case, you need to have O n times n, right? Okay, I would like you to think about that. If you need, you can go to the evening session. Okay, now let's check the question 9. We play on a local game show where you will complete n different challenges and trying to make as much money as possible. The ice challenge takes ti minutes to complete and starts with a value of vi dollars, but its value decreased by $1 per minute. In other words, if you complete challenge I at the time fi, you earn vi minus fi dollars, where the fi represents the time for completing the ice challenge plus the time of waiting other challenges to finish. Every challenge has a starting value, vi, is larger than the sum of all its ti. So you will make some money from each challenge. Your goal is to order the challenges to earn as much as possible. So usually this is the algorithm question, very similar, in the interview, most like that. So we give the story and we give you different condition inside of a story, and we also give you indicate what it is, what people wanted to do, what did they want to optimize. So here the have I challenges. For each challenge, we have n challenges, let's say n challenges, right? For each challenge, the ice challenge, and give you ti, it is the process time. Process ti, and also give you vi, that is value. And such that for these n challenges, you have 2n is kind of numbers. And the question here, let's say, give you example, right? Let's say we have task C1, C2, C3, and C1 process time, they have a process time. You may find that it's similar to the barrel heap, but actually it's different. So the C1 maybe 10 seconds, this is 5 seconds, this is maybe 15 seconds. And the value here corresponding to the 25 and 100, and I just give you random number. And doesn't have any correlation between the process time and the value. And here the people ask you, let's say here, if we process, this is process time, right? Let's say arrange the order. Let's say we have the order, right? Let's see. If you let C1 will come first, right? This is the T1 equal to 10. In that case, we have C2 and C3. They have the wait here. Let's use another color to represent the wait time. And they have a wait for 10 seconds. Wait for 10 seconds. Once this one finishes, you earn, let's say, P equal to V1 plus, and need to know, let's say here. This will give you example. So this have a file, this T2 got arranged, right? In that case, the C3 has to wait here. And then after the wait here, then you could finish. This is T3 equal to 15. And we see the value for this one, for the second one, which corresponding to V2 minus the wait time. This wait time go to the T1, right? And here, this is a plus V3 minus T1 minus, this is T1. This is T2 minus T2, right? So in this question, this is what we have, this example, and we have P is equal to sum of V for all the challenge minus the waiting time. And this waiting time minus waiting time, right? You may see this depending on what you choose, right? If that's true. If we want to maximize P, in that case, we have to minimize waiting time. How do you make sure the waiting time has been minimized? We want to make sure T, what you choose this one is the smallest one. And such that this problem is reduced to a sorting problem. On process time. On this process time, right? So it means if we sort this one, we see here, file should be the first guy to be processed. This should be second one. This should be third one. In that case, we make sure the total waiting time has been minimized. This is for this question. So you want to analyze this problem, find out which well-studied problem it can be reduced to. And this goes give the example here. Right? We see, and actually doesn't relate to V1, V2, V3. Really depending on the T, the process time. This is for first sub-question. What is optimal ordering for this one? You have to sort, you have to sort this one, right? Your friend claimed that if all the challenges have their value changed to the same value, same number V, it is well not to challenge the optimal ordering. Is this true or not true, right? Okay, so this is very obvious. Now let's check. We still have one more question. Sorry. And the last question, which is the question 10. In the question 10, which is bell heap, follow the steps in sub-question A through E. To finish the task in the paper, please take a picture of your solution and submit the picture. So this we want to try to check do you understand this bell heap or not, which is very elegant solution. First one, write down the letters in the box, and we save the root node in the array index 1. So it means W should be here. And let's draw this one here. So we have W, U, O, and we say the banner heap. First, it should be banner tree. Second, it should be complete banner tree. Third one, they should satisfy the ordering property, and elements in the this node should be this is the maximum heap, right? This is the maximum heap. we could have a binary, we could have minimal heap or maximum heap depending on how they define the ordering property. W is larger than all these children. This is a maximum heap. And so when we talk about the binary heap, maximum heap, and here we want you to to say what is representation in array. Let's see, we'll give more, right? And we see it here, and this is the index 1. It's index 1. And we want you to arrange the elements in the maximum heap in the array. And what we talk about it is we place the elements in each row by each row, and from the root row, from the first level to the last level. And for each level, we place the elements from the left to the right. So we have a W here, right? First one. Then we'll go to the second level, and from the left to the right, we have a U here, O here. Then same thing here. We have Q, S, G, H, I. With a binary heap, they use index to represent this elegant tree structure. Right? Can you see that? And W is the parent of U and O, and U is the parent of Q and S, O is parent of G and H, and I is the parent of G. The reason it follows completeness property, and this binary structure have very elegant way to represent the index, a very elegant the solution to represent given this index of parent nodes. If this is I, it should be what? If this is 1, it should be 2i in the left one, and if they have another one, 2i plus 1 in the right child, right? So this is the maximum heap. Okay, I should not give you details. Okay, write down the question B. Brief recite add the Z operation in the space available. So we have to add Z here, right? So we add Z in the binary heap. We first step, we appending this one in the end of the array. So we have a Z here. Let's use different color. So we have a Z here, right? So first make sure it's complete. Then later we want to swap, right? Make sure the ordering property is satisfied. We want to make sure the parent should be larger than what you have the child nodes. In this case, we have to swap. We have a Z here, Q here, and then do the same thing, right? And here, this one should be U here and Z here, and this W be here and Z should be here, right? So we have to make sure this we call about bubble up. You can see this procedure, right? Okay, and then the third step, the C, write down array-based representation, but after add the Z operation. So it means after this step you have to represent the array. And D, briefly recite the remove maximum operation in the space. Briefly write down the steps, draw the corresponding array-based representation and a heap tree-based representation for each step if in need. So in that case, if Z had to be renit, you have to be deleted, and we say in that case you have the hole here, right? So if you delete that, then you have a hole here. And then in that case, we make sure completeness property is satisfied. So we move the last element and place the last element as the root, new root. And then we have to check the children to make sure the order property is satisfied or not. We check the largest of the largest child and swap it. In this case, we think it down. So when you remove, we think it down. Think down the new root. So this is for remove, right? Think down the new, we call here, new parent node. If ordering property is not satisfied. If the ordering property is not satisfied. And this remove, if we add, we have to bubble up if the ordering property is not satisfied, right? So in the beginning, always we make sure complete property is satisfied. In that case, it is every element in the array, and real element has array, has been placed in the from the left to right in the array. Okay, I think this is the last question we would like to explain. And then, based on the student comments, some students said, since we have multiple short answer, multiple the file uploading based question, they would like to submit in the one place. So although this is 1 point, but actually this is just a dummy question. You really don't need to confused about that. We'll take a look, spend more time on that. You can submit all your solution here. When I check the solution, and then I will distribute your grades, your points for each this file loaded question to a specific place. I think that's all.